Okay, guys, so let's continue with the matplotlib library, which is very useful. We're going to make some elementary plots, and also there are much more complicated plots and sophisticated plots. Like, for example, if one works with large numbers or very small numbers, you can use logarithmic scale plots. But let's proceed with the simplest ones. There's a web page for a matplotlib library where you can see all the options and examples. I'm going to show you. So this is the website for the matplotlib library of Python. You can basically do everything. I'm going to mention a lot of different options for matplotlib, but if someone wants to extend his knowledge and his abilities on making plots, he can visit this site. Okay, so let's start with a very simple plot. I have a list here, variable x. It takes 13 values. So basically, the length of this, let's say, list is 13. And psi also has 13 entries. This is psi and y, and this is x. So I call the matplotlib library. So how do I do this? From matplotlib import pyplot as plt, or you can alternatively call the matplotlib library by using import matplotlib pyplot as plt. It's much more quick, this one. So let's call this. So this is the plot. Basically, it's poor. It doesn't have any labels. It doesn't have any grid or other options. It's a very basic plot. How do I do the plot? I call the matplotlib library. I define x and y, and I use plot equals plt plot x, y. And then don't forget to write down plt.show. So let's put some labels and some other features for the plot, for our plot. Let's see another example. For example, here I plotted two different curves. The first one is the same as in the previous case. So import matplotlib pyplot as plt and import numpy as np, because I want now some arrays, to plot some arrays. And this is very convenient and very useful for many for the next lectures, because when we are going to solve numerical differential equations, we're going to have NP arrays. So this is the first plot, and from the first day. We also plotted this earlier. So the second plot is basically is going to be generated by these points. I defined psi1, which is an NP linear space, taking values from 0 to 800 with 13 points. And I use plt.plot x, comma psi underscore 1. It's very important for the plt plot command to function that x and psi1 has to have the same dimension, the same NP dimension. So this is basically a list of 13 points, and this linear space is essentially a linear space with 13 points, but with different values, from 0 to 800. So these two commands are going to make the plots. Now, let's add some extra on the plots. We can add a general title on the plot, which is called by plt title, parentheses, and between these quotation marks, I just write the title of the plot. You can also add legends, and very important. The legend, what I say is that for a specific range of data, the plot is going to contain legends for the curves. So the first data is blue, the second data is orange color. It's very important that for this way that we wrote PLT title and PLT legend, the first data is going to be assigned to this data. So they appear hierarchical. They appear first in the commands. So first data corresponds to these plots. Hierarchically, they are first. So the second data is psi1, y1, and x again. So the title for this, the legend for this data is second data. So I call PLT X label in order to have labels on the X and Y axis. So PLT X label ages of children. This is the X legend, and PLT Y label the legend in the Y axis. And don't forget to call again PLT show. Okay, another more convenient way to introduce legends without caring about which is first, which data are first, and which data are last, are usually, this is usually done by using the label command in the PLT plot command. Label equals first data. And the same with the second plot, X, Y1, label second data. But in this case, the rest are the same. PLT title, just a random plot. PLT X label for the labels for the X axis and the Y axis. And before calling PLT show, it's important to call PLT legend. And this is because if I don't do this, it's not going to assign the legends to the curves. Okay, so let's run this. And let's run this without the PLT legend. So you see, if you don't call the PLT legend, it doesn't present the PLT legends on the plots. So this is the legend for the first data, and for the blue curve, and the orange curve, second data. There are options for the appearance, the overall appearance of the curve. It can be dashed, dotted, double dashed, or with a dash and dot, and several other ways that you can present the curve in order to discriminate the two data in an obvious way. Well, this is a continuous curve. It doesn't have any dashes or so, but you can add some extra features for the curve in order to make easier for the user to see the difference between the two curves. For example, in journals, if you publish in journals, and online you can see the colors, so the curves are different. But if you want to the printed version, which no color appears, then it's too hard to discriminate the two curves by just using these legends in grayscale. So you want to discriminate the curve. So the dashed curve is going to correspond, for example, to the first data, and the dotted curve is going to correspond to the second data. This is important. You can also see these extra features here in the matplotlib colors, specifying colors. You can define RGB or any other type of colors. There are some basic colors where I'm going to describe now. So one of the characters for the colors, you can use one of the characters P, G, R, C, M, Y, K, and W, which correspond, of course, to blue, green, red, cyan, magenta, yellow, black, and white. Also, there are some very important point markers that you can also use in the PLT plot command. I'm going to mention these. So you have a solid line, a dashed line, a dash and dot line, a dotted line style, and there are also several different markers that you can call in the PLT plot command. I quote them here, and I'm going to use some for example. Okay, so let's play with these commands. I can use this kind of entry in the PLT plot. So I used inside strings B and double dashes. So it's dust, dash, dust, dust, and B for blue, for example. Okay, I can use red or whatever. This is one way to introduce the color and the style of the curve. It's a direct method, but I don't personally prefer this because I want to have more command on the plot, but this is an example. So this is B, blue and double dust, 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 and the second one is red with dash and dot. So let's plot this. So you see, even if you have the plot in grayscale, you can discriminate the two curves. Okay, there is a more direct way to introduce color and the style. And you can do this inside the PLT plot command, which is color is assigned by the command color, which is blue, and the line style is going to alter, is going to change the final appearance of the curve. So this is dust, dust, and the second one, color is red, and the line style dust, dot. So let's plot this. So you get these two curves, which even in grayscale, if these are presented in grayscale, for example, in printed versions of scientific journals, you are going to have, you're going to easily discriminate the two curves by using the legend. Also, you can select a different marker for the plot. This is a quite big list for the markers. So let's use a marker, for example, in the upper plot, the first plot, the marker is D, and it is introduced by using the word marker equals, in quotation marks, D. So I'm using the marker D, it's here. I can also use hexagon and other markers. For the second, I use a hexagon, hexagon 2 marker. So let's make it a plot. So you see the differences for the markers. Okay, I can use also different markers. For example, a nice example is, for example, the plus sign and the circle marker with O or stars, maybe. So let's choose this one. So you see, it replaced everywhere the dots or the D markers with different plus signs. In the plot, you may have directly an RGB color. If you know the color, the code of the color, sorry, you can add a direct color in RGB style. So instead of color equals to blue or white or red or whatever with different initial small letters, you can use the code for RGB. So this is the first color and this is the second color. You can find online the colors. For example, if you type red in RGB code, so this is the different types of color in RGB. There are also some extra features for each curve. For example, the line width, the tight layout, and also you can introduce a grid for this plot. I did this here, and don't forget before the PLT show, call PLT grid equals to true. And the tight layout is introduced by this command, plt.tight_layout. So the style of the plot. When I mean style, I mean how the plot is presented. Python has a huge number of different styles that you are going to use. I just show you some styles here. Very elegant. You can always find these styles, the different styles. If you use import matplotlib.pyplot as PLT and print PLT style dot available. So Python is going to show you, going to present you the different styles that you can use in principle. You can play with this, find the best one for that suits your needs. It's a very nice, interesting. This dark background is very good, and the classic is also very good. And you can introduce the style just before the data. So after calling matplotlib library numpy, you can use the plt.style.use dark background. Okay, so it's a dark background here. You can also change this and make, for example, seaborne white grid. Doesn't look very good. Let's try some others. Solarized light. This, if I remember, it's very interesting for informal plots. Maybe seaborne paper. So there are various styles that you can use. You can call and see which are the available styles for Python, and you can use the one that suits your needs, what you actually need. Also, another by default style is this comic-like presentation, but this is for informal plots, or you just want to make some impression with this sketchy plot. And you can call this by using plt.xk c and d. So this is, in a way, in a comic way. It's not very serious for scientific journals. But this is a very nice style just to use it for example, for presentations among your students or whatever. You can also save the plot in various formats. Just use the same commands as before, but before PLT show, you can type plt.savefigure anaconda EPS. Or, for example, you can save it as PNG or JPEG. Always pay attention to the size of the saved figure as a file. You can change the analysis of the figure in a very simple way. Let's see. So this Anaconda PNG is now saved on the folder that Python functions on your laptop, on your Windows laptop or PC. So with PLT save figure, you can save your figure in various styles. In PNG, which is more convenient for good presentation, or JPEG, or even PostScript as EPS. Also, I'm going to show you how to plot a given curve for various values of a specific parameter on the same plot. I'm going to use a lambda function to define the function. So it's alpha np power x to the power of b. So you have the variable x, the parameter a, and the parameter b. X is the linear space between 0 and 0.6 with 300 points. The A list takes values 0.1, 3, 6, and 9, and the B list takes values in the range of 0 to 4. So if I use this command here for I in the range 4, y equals to the function j A list I, B list I for j in x, you can plot the curve x alpha times x to the power of b for several different values of a and b. So if I call this, I obtain this one. So let's stop here for some questions. I'm going to pause the recording. Okay. So let's also comment on another feature of the PLT plot command. This is an option. I used plt.ylimit. So this is going to limit the plot between 0 and 0.5. If I use, for example, 0.2, it just limits the y values from 0 to 0.2. I can also use this for the x-axis. I just type here x limit. So you see, I can constrain the curves, the values of the curves. Okay. Now it's a very important to show you also some logarithmic scale plots. I'm going to show you a professional plot. So basically, these are the sensitivity curves of primordial gravitational wave future experiments. These are the LISA experiment, the nanograph, the TSIGO, the BBO, Big Bang Observatory, the Einstein telescope, and square kilometer array. The data, I extracted these from the given sensitivity curves of several experiments, and I use some NP arrays to define the values of this physical quantity, which is the scaled h squared scaled energy density of primordial gravitational waves, and this is the frequency. So the frequency for me is an NP array. Which is defined here. This is a frequency, this is another frequency. And also for all the plots, I use a universal frequency if I want all the sensitivity curves in the same plot. So this is the frequency, these are the frequencies, and each sensitivity curve for each experiment is defined as HB LISA, HB DeSigo, HB DeSigo B, HBBO, and so on. So if I want to plot something in logarithmic scale, I use PLT log instead of PLT plot, and I use the frequency and the sensitivity curves, for example. Okay, so these are several different sensitivity curves. I also limit the PLT plot in the y-axis and the x-axis, and if I run this, this is the result. I forgot to run the initials. Okay, these are some extras. The sensitivity curves are this one. But I just mentioned this just to point out that you can also use log scale, logarithmic scale. So let's check an interesting feature for logarithmic scales. If you have the sensitivity curves in specific forms and specific values, for example, 10 to the power of minus 10, these are very small numbers. So you need basically logarithm. So you can fill in the various frequencies that you don't have a specific sensitivity curve. For example, if you check the LISA, which is the green one, it has sensitivity constraints only in this range of the frequency. So from 10 to the power of minus 5 to 10 to the power of 0, so on. Only for these frequencies, the LISA is going to give some results in the future, in 2035. So basically, what should I do in order to plot the rest of the frequencies? I just fill in with unity, with 1. And this is very simple to understand. Why? Because the logarithm of 1 is actually 0. So you don't have a plot for these frequencies. You only have a plot for the frequencies that LISA is going to yield some results. Let's see where exactly is it. Oh, okay. These are the sensitivity curves for LISA. Okay, so these extra options for logarithmic scale plots concludes the lecture on matplotlib. So let's go to the core of these lectures, the numerical analysis and how to solve systems of ordinary differential equations with Python. Python offers a fantastic way and more efficient way to solve differential equations compared with software packages available online. And this is very useful, Python, because it's free. And also you can have a direct command on the different steps of integration. Usually you use some softwares available, use some Runke-Kutta approximations of 4 or 5, fifth order. You can have with Python a direct command on the system that you are going to use in order to solve the system of differential equations, the method. You can define explicitly the method. And sometimes you have stiff problems that cannot be solved easily with Runke-Kutta approximations, so you might need something more efficient, for example, LSODA, sorry, or Radau, or some other fancy methods of solving differential equations numerically. So in most cases, I'm going to use the solve IVP command of Python. So solve IVP is very important. It has several features that I'm going to explain in brief shortly. But before of that, it is very important to note that Python can only solve with solve IVP systems of differential equations of this form. So basically, psi y here is an array, an n-dimensional vector. So you have values that takes, y takes the values y1, y2, y3, and yn. So basically you have the derivative of y1 equal to f1. F is also an NP array, an n-dimensional vector. So you have a system of n different differential equations. So you have the derivative of y1 over t equals to f1 t, which is a variable, the integration variable, and y1 here. So you can imagine that you are having actually n different first order differential equations. With second order differential equations, you can also use Python to solve it if you use a trick. If you have a second order differential equation, for example, this one here, how is it possible to make this differential equation first order differential equation? You introduce a new variable, which is for us, if x is the distance, I introduced the variable v, which is the velocity, which is equal to the derivative of the distance over t. which is this. So the second order differential equation here is transformed to a first order differential equation. This is a very simple problem, but it's very useful to understand how Python is going to solve this system of differential equations numerically. What is also very important is to have an initial condition, and this y is an n-dimensional y0 is an n-dimensional vector with n different values, and these are initial values essentially. Also, it's very important to respect the hierarchy of the appearance of the variables. So t, the dynamical variable, must appear here first in the program, and psi, y, it has to appear second. So let's proceed directly to a nice example in order to understand how Python works. I'm going to use the solve IVP module, which basically applies a dynamically 5, but essentially fourth order Runge-Kutta integration method. But there are also several different options for the integration method, which I'm going to explain shortly. So let's consider first a very simple problem of physics. You have a ball of mass 1 kilogram, which is dropped from an altitude of 10 meters above Earth, free fall to the ground without any friction. If the initial velocity of the ball is 0, find the position of the ball at all times and the velocity before it touches the ground. V is equal to 10 meters over second square. Very simple problem. The differential equation is governed by Newton's second law. So basically, this is a vector, the force, and this is the second derivative of the distance. The initial condition we have is that x equals to 0, x at time 0 is 10 meters, and the derivative of x, which is the velocity at time 0, is 0. The analytic solution of the problem is this one. So if you use the initial conditions, you actually get this solution. So I have the analytic solution, and I'm going to solve numerically the problem in order to see how accurate Python is, just to exemplify the solve IVP method. So the first step that we must do is to transform this set of this differential equation into a set of first-order differential equations, because Python only understands first-order differential equation. How can we do this? We just use the variable v, which is the velocity. So if I use the variable v, the differential equation becomes the derivative of v over t equals to minus g, and the derivative of x over t is equal to the velocity. So it's of the form derivative of y over t equals to f of t of y. The function, the variable y is an two-dimensional vector which takes values x, the first value, and v is the second value. So check out this one. These are the values of the variable y, x and v. And the function v, f, is equal to v and g, which is basically the right-hand side. Let's solve this with the solve IVP module command. Basically, the solve IVP integration method has several different entries as options. The most important is fun, which is basically the function f. It's another important entry is tspan, the initial condition, which is y0, the method, the integration method, the t evaluate, and the rest are not so important. These are more fancy, but this is very important, the t evaluate. This, let's explain this in some detail by using an exemplification. So this is the analytic solution. Let's show this very simply, very quickly. I'm going to solve this to plot the analytic solution. I'm going to compare the analytic solution to the numerical solution. So I introduce NumPy and the matplotlib. I define the function x of t, which is this one. And this is an internal variable. This is not a global variable. It's defined inside the function xp. And the function xp is equal to this expression, which is basically the analytic solution, this one. Also, I define a dynamical variable. The dynamical variable is t, the time, and I need, for example, 101 points. From 0 to final, to t final, which t final is this one, np square root 2. I define the function xp of t. I assign this function to the variable xs, and I make the plot of t, which is this linear space, and xs, which is basically the function xp of t. I use specific markers, and I use the label xt analytics. So if I make the plot, I obtain this plot here. So let's proceed to the numerical solution. And this is very important. I import NumPy as NP, matplotlib again as PLT, and from SciPy integrate module, I import the solve IVP, which is basically the numerical method I'm going to use in order to solve numerically the differential equation. So my differential equation is this one. Recall the differential equation. And I'm going to write down in a Python style way how to express this set of differential equations. So I define the function f first, which is very important for the solve IVP. The function f is going to be the first entry in the solve IVP command. So I define the function f. Notice the hierarchy of t and y. Y is going to take two values. Y0 is going to be assigned to the velocity, and y1 is going to be assigned to the distance. The two local variables defined inside the function f is g and the mass. The set of differential equations are basically these two, the v over the t equals to g, and the derivative of x with respect to the time is equals to minus v. The function f is going to return an NP array, which is a set of two entries. First, the first entry is the derivative of v, and the second entry is the derivative of x. Now, I defined the final time that I want the system to be integrated. So the final time is np square root 2, as in the analytic solution. Now, t-span is basically a range of values. So t-span is basically an NP array with two entries. The first entry is 0 times 0, and the last entry is tf, tf, t final. Now, very important, I defined the integration path. So basically, I defined the variable t. The variable t is going to take values from t-span 0, which is basically 0, until t-span 1, which is basically tf final, t final. I could use it directly here. and I want 10 points in this interval. Now, the initial condition. The initial condition of the variable y is an NP array with two values. The first value, recall, is the velocity, psi0, y0. And the last, the second entry, which is basically x, is the second variable, the initial condition for the second variable, which was 10 meters. So y0 is an NP array with two entries, 0 and 1. These are the initial conditions. Now, let's proceed to the solve IVP method. I define the solution as solve y. And I use solve IVP, which I called here, with SciPy integrate. First entry is the function f. So basically, this is the definition of f. The second entry is t-span, which is basically, let's say, the values of the initial values and final values of the integration variable, which is t, the time. Y0 is the initial condition. It's defined after t-span. So this is the initial and the final value of t-span, and this is the initial condition. Method, you can use Ruke-Kuta for dynamically 5, or other methods. I'm going to describe these later on, like L-Soda or Radau or BDF or some other method. If someone uses, if the differential equation is stiff, you are going to use basically some L-Soda or Radau method, because the Ruke-Kuta actually works and functions perfectly if you don't have a very stiff system of differential equations. But this is a very elementary that we're using now. It's very simple. So I'm just going to use a Ruke-Kuta integration method. And the last and important entry in the solve IVP command is the t-eval, which is basically the final, the interval of values of the dynamical variable, which is the time interval, linear space from t-span 0, which is 0, until t final, with 10 points. So basically, this t-eval has 10 points for t. Now, how to obtain the two different solutions? I'm going to obtain two solutions here. The first is v, and the second one is y. So v is assigned to the solution dot y0, 0. This is why I used here y0. And the solution x is going to be assigned to the solution, which is this one, y1, which is this one. So basically, v is the first component of the solution, which is the solution here is actually an NP array with two entries. The first is the velocity, and the second one is the distance. I am going to also plot here the analytical solution. So I'm going to rewrite here the analytical solution and the plot. And now I'm going to plot the numerical solution, which is basically introduced by this PLT plot, time interval. So these are the values of t. And the second one is x, which is defined here as the solution, the second entry of the NP array of the solution sol y. And the rest of these are just extras for the plots. So let's run these two. These are overlapping. You cannot see it. I'm not sure if you can see this. I'm going to change the color. So let's make this one red. The analytic solution is red, and I'm going to make this one, let's say, blue. So you can see here the red curve, which is the XT analytics, and the numerical curve, which is exactly overlapping with analytic solution. So let me demonstrate again in order to have it in the video. You can pause it and you can generate again the same exercise. So basically, you import numpy as np, matplotlib pyplot as plt, and scipy integrate import solve IVP. You define the function, the right-hand side of the differential equations that you are going to solve in this way. I define the final value of the time, the t-span, which is the range of the initial and final value of the t variable, of the time variable, the time interval, which is basically a linear space with 10 points. I can increase this one if you want. The initial condition, I call the solve IVP command in order to solve numerically the differential equation using the method Ruge-Kutta 45. I define the solution, the outcome, as V, the first entry of the NP array solution, and the second entry is X. And then, using the PLT plot, I plot the numerical solution here for X. And I also plot the numerical solution for I'm plotting the analytic solution, which I defined here, in order to have this in the same plot. If I use here V, I'm going to plot the velocity, okay, which is the second entry here, the first entry, I'm sorry, in the solution. Okay, let's change this one. And then the plot is very easy to be done. PLT title, PLT label, PLT Y label, title layout. I just introduced a grid and a legend. And then in the end, I just use PLT show, and the result is this one with complete overlap. Let's also present the same example by more steps of analysis. I could introduce directly an NP array like this one, but I wrote it in this way in order to have clarity in the various steps. An important point is the interval of integration. The as-solve IVP starts from t equals to t0, which is basically t-span 0, and until it reaches the final, which is t-span 2 entry, which is an NP array. Okay, let's discuss a little bit about the different methods that we can use. These are fancy methods. The most fundamental is the Ruge-Kutta. There are different other methods like the Radau, the LSODA, which is Fortran-based solver appropriately designed for Python, the BDF, which is also for stiff systems, and the Radau again, which is also for stiff systems. LSODA is the best for me, and the Ruge-Kutta for fundamental problems. But LSODA usually solves everything. I have some stiff examples that we will do in the next lecture, but not this week. But next week, I'm going to show you how LSODA is going to simplify the problem. Now, some extra details before we close this lecture. Let's see an interesting comment. If I want to find the analytic and numerical values of the variable x at the end of the time, so at t equals to 10, how can I do this? Basically, recall that I defined the time interval to be a linear space, NP linear space, from t0, t-span 0, so from 0 until t final, with 10 points. So if I use time interval 10, basically it's going to be the final value of time interval. So if I use x10, x10, which x is defined here, it's going to obtain the value of the variable x at t span 1, so the 10th entry. So if I want to find actually the 10th entry, I'm going to use print x9. And why I'm using 9 and not 10? Because it also counts 0. So from 0 to 9, these are 10 entries at t equals t span 1. And if I also print here v9, it's basically the value of the velocity at the 10th point of the time interval. So basically, it's v9. And if I want to find the final time, I just print the final time is plus sign, like concatenation of strings, plus string t1, which I defined here as the linear space with 10 values, 10 different points from 0 to tf. So basically, it's going to define to return tf, which is square root of 2, which I defined here. Okay, now, before we close this lecture, another interesting point. Sometimes you can use in the plot here, you can use the time interval as I did in the previous example, or t final here. T final, let me show you this example here, or the time interval. Time interval is equal to this linear space. And I also plot x for each time variable. I plot the corresponding x value. So I have 10 points here and 10 points here. I can also introduce a universal variable t by using the time interval and use t instead of the time interval. This is a matter of perspective and maybe a matter of taste, if you want to use just t. So if I define the time interval again as this one with 100 points at this time, and I define globally t equals to sol y t. Basically, what Python does is I make Python understand that the time variable t is defined as at the plot points of the solution psi, y. So basically, I have 100 points here. Y is going to have also 100 points, and I define it as t equals to sol y t. So basically, the system assigns 100 different values to the variable t, spanned from the solution sol y. And if I use plt plot, this is the command here. So basically, I don't have to use time interval, but this is a matter of taste, as I said. It's not very important. Okay, this is another way. Let me see what I get. Okay, this is another way. Yes, I already commented on this. So let's finish this lecture here. In the next lecture, I'm going to solve some non-trivial stiff problems. And also, I'm going to solve in an inverse way, in a reverse way, the same set of differential equations. So let's stop here and let's have some question session.